The first semester of classical mechanics. This is the semester summary. So I'm going to go over the key ideas that I covered, and this is at the end of my playlist. The playlist for all my videos are down below. You might want to watch this at the beginning, but it might not make sense. But you can't just get the whole course out of this video. I mean, there's a lot of stuff. You gotta do the work. And this is the book that I'm mostly using. Yes, my book's all beat up because I've taught it quite a few times. And I'll tell you the chapters from this book. I'm not sold on this book 100%. After you teach things a certain number of times, you kind of want to do it your own way. And so maybe I should just write my own material. I don't really even know. Let's just get to it. So this is the first semester. And I didn't follow the chapters in the book exactly because for us at my institution, students don't always take the second semester of classical mechanics, and I think the most important thing for them to get out of classical mechanics is Lagrangian mechanics. And so I made sure that's in the first semester. Let's get to it. So I did start with chapter one, and I do have my notes here. Okay, so see, it says classical mechanics up there, but now I can erase that because we're in chapter 1, Newton's second law. Let's just say it as Newton's second law. Okay, so Newton's second law, in this chapter, we're really looking at this, F net equals mass times acceleration. And we do a couple things, but I'm going to go ahead and just kind of set up a problem, a very simple problem, and then we'll do a more complicated problem, and then that will kind of understand where we're going with the whole thing. So we do have to solve differential equations in this section. So imagine that I have a ball, and it starts with an initial velocity v0 in some x and y direction. How do I do this? Well, I know I have a downward gravitational force mg. What do we do? Okay, so I can say my position vector r is equal to x hat plus y hat. And I'm doing this in Cartesian coordinates because when we do it in polar coordinates, you can see the difference. What about the velocity? Well, the velocity is dr dt. So I have to take the derivative of this vector, and this is in 2 dimensions. You could do it in 3 if you wanted to. And so the derivative of x hat is going to be x dot x hat plus y dot y hat. And we have a very important thing here that you will see is not always true, in that x hat and y hat are constant unit vectors. They don't change. So I don't have to worry about taking the derivatives of those. The next thing is this dot notation comes up all the time in classical mechanics. The dot notation, one dot means the first derivative with respect to time. Second dot means second derivative with respect to time. Okay. So that's my velocity. And then my acceleration would just be the derivative of the velocity. So you can actually write this as r vector double dot. Now that's a 2 hat notation, right? So it's got 2 hats on that variable. I don't like to do that, but sometimes you have to. But you don't have to do it here. But anyway, x double dot x hat plus y double dot y hat. Now, if I take that and plug it into Newton's second law, I have, let's write the net force as negative mg y hat plus 0 x hat is equal to mass times x double dot x hat plus mass y double dot y hat. So I actually get 2 equations, right? I get an equation for x and an equation for y. I get x double dot 0, and I can integrate that, right? I can integrate both sides of this equation. Now, you can't always do that. When we do simple harmonic motion, which I do in this chapter, you have to kind of guess at the solution. But you can see where this is going. So if I integrate both sides of this, let's just write this out. I'm going to write this as dx dot dt equals 0. And I can multiply both sides by dt, and I get dx dot equals 0 dt. And if I integrate both sides, I get x dot equals a constant. And if I plug in at time t equals 0, the velocity is 0, this is going to be v0. Now I can do it again, and I get another constant, and you get this. I'm not going to do it. This is a summary. X equals x0 plus v0 t. Yeah, that's what you get. Okay. Now, if I do the same thing for the y component, you get other constants, and you get y0 equals y is y0 plus, this is vx0, vy0 t minus 1/2 gt squared. So when you integrate, that's really important. When you're solving these differential equations, you integrate twice, you get two constants. You get those two constants from the initial conditions, the initial velocity and the initial position. Okay, that's easy. We can do a bunch of problems like that, and we will. But now, what if I change this to polar coordinates? So I can say in polar coordinates, I can define the vector with the angle theta. They use phi, and there's a difference between polar coordinates in physics and math. So don't worry about, if you want to use phi, use phi. I grew up with theta, I use theta, but you do you. Okay. So we can change this stuff. Again, I just want to remind you, this is a review. Okay. So here I'm going to say the vector r, the position vector, is r hat. So this is my r hat direction, and this is theta hat direction. Now when I take the derivative to get the velocity, I can say the velocity is dr dt, which is r dot r hat. But wait, if this thing is moving, r hat is not constant. So I have to add plus r dr hat dt. Now, how do you deal with this whole situation? How do you find the derivative of a unit vector? Well, we do some tricks here. We're going to say we're going to mix Cartesian and polar coordinates. I can say r is x. No. Yeah. No, wait. No, it's going to be r cosine theta x hat plus r sine theta y hat. Right? So I'm going to use the x hat and y hat Cartesian unit vectors, but the polar coordinates. So I'm going to do a mix. And then I can find these unit vectors. I can say r hat is the partial of r with respect to the variable r, then I have to normalize it. So the magnitude of the partial of r with respect to r. And if you do that, you get cosine theta x hat plus sine theta y hat. But now I can take the derivative of this with respect to time. And if you do that, you find that the derivative of r hat with respect to time, I'm not doing this whole thing because I have a whole video on it, is, I'm going to write it down. I wrote it down. It's theta. Where did I write it down? I think it's, okay, I'm not going to write it down. I thought I wrote it down. Well, anyway, you get some other expression, and I think it's theta dot r theta dot theta hat, or well, don't worry about it. You get something. So then you can take these derivatives. You can write this in terms of r hat and theta hat. You can do it again. You can get the acceleration, and we get the acceleration in polar coordinates to look like this. The acceleration in polar coordinates is r double dot minus, I always get this wrong. I'm looking it up because I forget. Minus r theta dot squared r hat plus r theta double dot plus 2 r dot theta hat. So now I have the acceleration in polar coordinates, and so you can do a bunch of great stuff. Why would you even care? So just to point out, this is why you care. If I have a pendulum like this, well, if I use polar coordinates, it only has one variable that changes. R doesn't change. R is constant. So R double dot 0, R dot 0, and it makes the problem a little bit easier and more manageable, and you can get an expression in terms of theta. And I'd like to come back to the pendulum because we do that a bunch of times. Now, you could do the same thing for spherical coordinates. Things get out of control rather quickly, but that's that. So Newtonian mechanics works best if I can actually calculate the force, even though I can't calculate that tension here, but I just did a trick to get around that. That was chapter 1, right? Okay. Moving right along, chapter 2 is, I already forgot, what was chapter 2? Chapter 2 was velocity-dependent forces. Okay, there's not a lot to say here because it was mostly just a bunch of practices. This is velocity, I'll just put velocity forces. So we looked at things like this. Suppose I have an object moving with a velocity v that way, and there's a force, a drag force pushing backwards that's proportional to the velocity, such that the magnitude of the drag force is b times v. Then how do you solve the motion for that? This one actually is pretty easy. Let's just do this one, and then I'll talk about the other ones. So if I use Newton's second law, I can say F, in the x direction, I'm only in one dimension, F net is negative bv. Let's say it's moving in the positive x direction. The force is in the negative x direction. And that's going to be equal to mass times acceleration, which I can write as mass times dv dt. Now, we can actually get an expression for the velocity by multiplying both sides by ddt and dividing by v, and I get dv over v is negative b over m dt. And then you can integrate both sides, and that's not too hard, right? Because this is the natural log of v, which doesn't make sense just yet. And this is negative b over mt. But then if I use my initial conditions and take the exponent of both sides, I get v as a function of t is the initial velocity times e to the negative b t over m. But I'm not going to do all these problems. I'm just telling you where that one comes from. Now, the next thing that we do is we say, OK, that was fun. Let's do a dropping ball. So it has a gravitational force and then the drag force upwards. And how do we solve that? And here we use a trick. We say mg is bvt. So that's the terminal velocity. And we can rewrite the problem. We can rewrite Newton's second law in terms of this new velocity. Or a u substitution, and you can solve this problem. It's not that bad. Okay. Then once you have that, once I have a vertical and horizontal motion, you can actually do projectile motion with linear drag, because the drag force in the vertical direction and the horizontal direction can be separated, and so you can just treat it as two separate problems, just like you do with normal projectile motion. And then we say, okay, what about this? What if the drag force, I'll write it as the magnitude of the drag force, I said magnitude, is cv squared. We call that quadratic drag. How do you deal with that? It's not too terribly difficult if you have a horizontal with no gravity. Vertical with gravity is a bit, okay, but you can do it. But the thing here is that since the drag force is proportional to the velocity squared, that means that the x component of the drag force depends on the y component of the drag force, because we have to find the magnitude. So you really can't do projectile motion. You can do it numerically, and we did. I did a lot of numerical stuff in this course. We used Python to solve it. And in fact, you would write the drag force as negative c times the magnitude of the velocity squared v hat. You have to use that unit vector to get the direction. So that's velocity-dependent forces. Pretty fun, huh? Okay, next, I went to chapter 4. I did not do chapter 3 on momentum. And I think for me, looking at the momentum, there's a lot of great stuff in there. But momentum, they focused on like the rocket equation, which I'm not a big fan of, because it's just kind of like, you know, momentum's conserved and that's cool. I just didn't do it. So, sorry. But I did go to chapter 4, work energy, because we can do things that we didn't do in our intro physics course for the freshman level. So we have chapter 4, work energy. So the first thing was to define work as the integral from 1 to 2 of f dot dr. Now, this can be a new thing, right? In the first semester of physics, work energy was like only in simple situations. But now we can do crazy situations. Suppose I go from 1 to 2 down here, and I go along this curved path like that. Then how do I do this? Well, in Cartesian coordinates, dr is dx x hat plus dy y hat. So I can do the dot product. So f dot dr is fx dx plus fy dy. Now notice that fx, it is possible that fx depends on y, right? That's just the x component of the force. It can still have a y value in there, and the same thing for y. So if I do this, I actually get two integrals. I get this fx dx, which can depend on y, plus fy dx. And this is, we'll do this over x, and we'll do that over y from here to there for both of them. Now the trick comes in is, what if you have an x force in your y integral? Well, then you have to use the equation of this line. Let's say it's x equals 3, y equals 3x squared minus 2x. I don't know. But now I can take the derivative of this and get I can either take the derivative of this and get a function of dy in terms of x and plug it in. Plug it in here, or you can substitute in just y. But you can convert each of these into just x's and y integrals, and that's how you do a line integral. The work energy theorem says that the work done on an object is equal to its change in kinetic energy, where T is 1/2 mv squared. So get used to that T. We use T for kinetic energy, not K, because we want to look cool. Okay, so we've got to do something a little bit different to say, hey, we're not like normal stuff. We're doing something different. I don't even know why we do that. Now there was a special case. If I take some path integral down here along that path, and then I go back along that path, and then if I do the whole loop around the thing and I get the work as 0, for every possible case, then it's a conservative force. And so we have two tests for conservative forces. I can say the partial of fx with respect to y minus the partial of fy with respect to x. If that's 0, then it's a conservative force. Now in 3 dimensions, we'd say the magnitude of del cross f is 0. And here the del operator is the partial in Cartesian coordinates. Partial with respect to x, x hat, plus the partial with respect to y, y hat, plus the partial with respect to z, z hat. So if that's true, then it's conservative. And if it's conservative, then I can say this work done by the force is a potential energy. So U is technically delta U as a function of the position will be negative the integral of f dot dr. And then I can go backwards and I can say F is negative del of U, where that's the del operator on that scalar value. And that's work energy. See? This class isn't so hard, right? Okay, next I skipped ahead again. I went to chapter 9 for non-inertial reference frames. Mostly because I thought it'd be fun to talk about tides. And so, you know, I think the big meaty chapters are chapter 1, for me, chapter 4, but velocity-dependent forces and non-inertial frames are just a bunch of problems, really. Not a huge big ideas. And then we'll get into chapter Lagrangian, which is 6 and 7. So this is non-inertial. So just remember that we can write Newton's second law, F net equals ma. And if the acceleration is measured in an inertial reference frame, this works, right? So that means that the reference frame where we measure the acceleration is not accelerating. It can be moving, it can't accelerate. And if it is accelerating, then this doesn't work. So how do we fix that? We can fix that by adding in a fake force. So, or fictitious if you want, I like to call it fake. F fake is going to be equal to negative mass times the acceleration of the frame. So the simplest case, imagine you're in an elevator and the elevator is accelerating up and you want to use Newton's second law in here. Well, you'd have gravitational force down and then you'd have some other fake force down, and then you could treat that as just normal Newton's second law. Now, if you have the case of a rotating reference frame, then it's not so easy, right? For a rotating reference frame with an angular velocity capital omega, that's the frame rotation, then F fake is going to be F Coriolis plus F centrifugal. So the Coriolis force is going to be equal to, I forgot, is it negative? No, I have 2 m r dot cross omega. So this is the force that depends on the velocity of the particle in the frame and the acceleration, the angular velocity of the frame for constant acceleration. You can derive this. It's not super easy, but I did it for you. And then I have the centrifugal force is going to be equal to, again, looking, is it negative? No. M omega cross r cross omega. So you got to take this cross product and then do another one. This turns out to be the same as F Coriolis, F centrifugal. The magnitude is m r omega squared, the angular velocity. So you've seen that before, right? But it points away from the center of the rotation. We also talked about the tides. I just want to mention the tides because, like I said, the tides, here's the Earth, here's the moon, totally not to scale, and you get these two tides. And it's not because of a differential in gravitational force. It's because the Earth accelerates that way, right? And so this is a non-inertial reference frame. It turns out that the fake force on this side plus the gravitational force gives you that one bulge, and the same thing is true over here. So that's why you get two bulges. You can explain the two bulges there by using a fake force. I thought it'd give me a double thumbs up. It used to. There it goes. Okay. We're not done yet. So we do have one more chapter, and that's the Lagrangian. So there's a chapter on the variational principle. I didn't cover that. That chapter derives the Euler-Lagrange equation, which I think it's a hard derivation, and I really just want to use it. Again, I'm trying to get students to be able to understand Lagrangian mechanics. So let's just talk about why you would do Lagrangian mechanics and then what it is. So the pendulum's a great example, right? If I wanted to use Newtonian physics here, F net mass times acceleration, I totally could do that. I totally could, and I did, okay? But it's kind of a cheat because I don't actually know all the forces, right? I know there's a gravitational force pulling that way, and there's a tension that way. But that tension force changes in direction, changes in magnitude. It's what we call a force of constraint. It's, I'm going to do whatever I need to do to keep this mass from moving too far away, from moving greater than the distance r. So if we use polar coordinates, we can get it to work out where we don't even care about the tension. That was the key there. And the pendulum is such a hard problem. And it's always in introductory physics courses, and it really shouldn't be because it's just too complicated. So I wouldn't put it in there. And I don't. And then you can show simple harmonic motion if it's small, blah, 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 blah. So, but what Lagrangian mechanics does is it says that we don't even need to know about the forces. We can just say, I can make up a new set of coordinates for my system called generalized coordinates. And I can create equations of motion from those generalized coordinates. So the first thing to do is to say the Lagrangian is kinetic energy minus potential. And this all comes from this idea of the principle of least action, which I'm not going to go into because I want to focus on using that. So here we're going to say we have some variables, some generalized coordinates, qi, right? So it could be q1, q2, q3, x1, theta, r, you could whatever you want. It doesn't really matter as long as they describe the system. With that, I get the following different equation of motion, not equation of motion. This says that the partial of L with respect to qi minus the derivative with respect to time of the partial of L with respect to qi dot is equal to 0. And from that, I can get equations of motion. If I have just one generalized coordinate, I get one of these equations. If I have two generalized coordinates, How many of those equations do I have? That's right, 2. Okay. So in this case, you could say theta is your generalized coordinate, and you would get the following. The partial of L with respect to theta is minus the time derivative of the partial of L with respect to theta dot is equal to 0. Now, the trick is T, right? How do I get kinetic energy in terms of angle theta? Well, we always write this as x dot squared plus y dot squared, and then I can say x is r. In this case, it would be r sine theta. And then y would be minus r cosine theta. And I can take the derivatives and then plug it in there for both t and u. And you can get your equations of motion. And that's what we did. We did a lot of practice with that, and it was awesome. And I still have more problems to do because I like it so much. Okay. Now, there's one more thing in Lagrangian mechanics that we did, and that was finding the force of constraint. What if I want to find the tension? In that case, I under-constrain the system. This only has 1 degree of freedom, but I'm going to under-constrain it. I'm going to give it 2 degrees of freedom. And then I'll say, I'll write my kinetic energy and my potential, and I'll get my Lagrangian. And then I'll write my force of constraint, in this case, F of r and theta would be a constant. So this would actually look like r equals r. And then I can use that to say the modified Euler-Lagrange equation, the partial of L with respect to r plus lambda partial of f with respect to r is the time derivative of the partial of L with respect to r dot. And the partial of L with respect to theta plus lambda partial of f with respect to theta equals the time derivative of the partial of L with respect to theta dot. And so here, the force of constraint in the theta direction is lambda partial of f with respect to theta, which is 0 because there's no theta there. And this is the constraint in the r direction. So you can find those forces of constraint with that, and that's that. Okay. Now I'm going to give you a double thumbs up. There we go. So that is Lagrangian Mechanics Semester 1. I didn't include any of the Python stuff, but again, the playlist for all my videos are down below. I'm going to put some of my materials online somewhere so that you can see the whole structure of the course in case you want to use it. You're more than welcome to use whatever you want to use. This is on YouTube. It means you just use it, right? And then for the second semester, I think I'm teaching the second semester. And so what am I going to cover? What is in store for the second semester? Well, I'm going to start off with more Lagrangians as a review, and then do the central force problem so we can do orbital motion. The two-body problem is really great. We'll definitely talk about the three-body problem and how we'd have to do it numerically. Talk more about Hamiltonian, coupled oscillations, rigid body rotations, and then something else, probably maybe chaos. I don't know. I'll definitely do stuff from the book. I'm not sure. I'll probably let my students decide what things they are interested in, and we'll do that. Okay. Hope you studied for your final. I'll see you next semester.